Hello, and welcome to a video presentation of our ECE140 final project. The purpose of this project was to design a logical circuit using VLSI techniques. The design was then implemented using the electric VLSI software. Due to the team's familiarity with digital logic and the benefits of working with the finite state machine, a vending machine, driven by an internal finite state machine, was selected. An essential part of the project was to create a schematic and layout utilizing CMOS technology, specifically 300 nanometer rules. Our team decided to use a state machine driven approach. A finite state machine is a model used to design both computer programs and sequential logic circuits by using states, usually in the form of bits, to keep track of past inputs. This vending machine utilizes a state machine to keep track of the money that has been deposited by the user. These states, in addition to the encoded input, are then used to determine the next state and possible outputs and/or flags. Some critical components include JK flip-flops, which serve as memory for the finite state machine, a 4-to-2 encoder to convert input signals into binary, and a rising edge triggered pulse generator to serve as a clock and for debouncing purposes. The team chose the following specifications. The target price for an item would be $1. The inputs would be return, quarter, dollar, and buy. A purchase would only be able to be made if we were at or above the target price, and adding additional money would have no effect, which means that any money will be rejected and returned to the user. Next, the team settled on the idea of using a finite state machine to realize the functionality of the vending machine. Each state in the state machine would correspond to the number of quarters deposited into the machine. For example, state 3 means that there are 3 quarters, while state 6 means that there are 6 quarters, or $1.02. Based on the specifications put forth by the team, a minimum of 8 states were needed. It was realized that these 8 states could be represented by 3 bits and consequently 3 flip-flops. The team had initially decided to implement D flip-flops, but came to realize that it would be more advantageous to instead utilize JK flip-flops. It was decided that the inputs would be encoded through a 4-to-2 encoder. Return would be encoded into binary 0, quarter would be encoded into binary 1, dollar would be encoded into binary 2, and buy would be encoded into binary 3. Based on the specifications put forth by the team, this was the state transition table that was produced. This state transition table was used for the Carnot maps that would produce the logical equations our group needed to drive the J and K logic networks in the state machine. From the Carnot maps, it was possible to derive equations for each of the inputs of the JK flip-flops. On the left is the J logic network that drives the J inputs for each of the flip-flops. On the right is the K logic network that drives the K inputs for each of the flip-flops. All that was necessary to finish the state machine was to feed the outputs of these networks into the 3 JK flip-flops and add a positive edge triggered clock. This is the layout in electric VLSI of the J logic network. The team attempted to condense the layout as much as possible, and in our endeavor we realized that adding a second layer of metal would help facilitate the construction of this network. This is the layout in electric VLSI of the K logic network. At this point in the project, we realized it was to our benefit to utilize one layer for horizontal connection and the second layer of metal for vertical connection, allowing for easier interconnection of the logical gates. This is the layout in electric VLSI of the 4-to-2 encoder. We initially decided on a priority encoder, but quickly realized that in real world, no 2 inputs would simultaneously be up at the same time. Thus, to save space and use less transistors, a standard encoder was constructed. It should be noted that the D0 is connected to ground, since the D0 input and no input at all is essentially the same thing. This is the schematic and layout of the pulse enable. It is constructed using an AND gate with the input and its inversion feeding into it. This design takes advantage of the time delay resulting from the 3 NOT inversions to create a 30 nanosecond low to high pulse. Consider the case where the input is initially low and the inversion is high. Because it is an AND gate, the final output will be low. Once the input is switched to high, because the inversion input has to go to 3 NOT gates before going low, the output results in a high. Thus, a rising edge triggered pulse enable was produced. This is the final vending machine layout. Here we can see all of the main components of the vending machine. The 4-to-2 encoder is at the upper left section of the layout. The input detector, which acts as a clock to the JK flip-flops in the state machine and utilizes 5 NOT gates for delay, is at the lower left section. The significant output flags, such as dispense or reject money, are found at the upper right section. The change dispenser is located at the lower right section, and the state machine is directly in the center, bridging the inputs to the output signals. Here's a table of all the main components and building blocks of the vending machine. The table includes the min and max delay generated by the cell. Due to the nature of the state machine, certain processes occur in parallel, which makes the timing somewhat difficult to analyze in most cases. Some transitions in the finite state machine occur at different speeds because not every input causes an output change, and certain outputs are dependent on the machine's current state. A problem was initially encountered when attempting to trigger the flip-flops using the NOR4 as the clock by itself. The clock was faster and not dependent on the J and K logic, meaning that the clock would always trigger before the logic networks would stabilize at the inputs of the flip-flops. As a result, the finite state machine was never able to leave state 0. Therefore, a series of inverters were chained together to delay the clock pulse, allowing the JK logic to produce the proper inputs before flip-flops were triggered. Because of the team's familiarity with digital logic and finite state machines, the design itself was not as challenging as was previously expected. Creating the layout and debugging proved to be the most troublesome aspect, but these problems quickly resolved. Thus, a working vending machine was implemented using the VLSI techniques learned in ECE140. The state machine portion of the design is standalone, but the team was able to incorporate additional features such as a change dispenser and other useful flags. These output signals can be coupled with mechanical systems to create a final vending machine that is more recognizable by the average consumer and easily deployable in mass production by any company.